Well, you now have a chip out. Could you just sort of give us a quick overview of what it entails and why it is different?
hmm Well, absolutely. And I have one here. Of course, since this is a video interview, I'll have to hold this up. Here's the eval kit for the Electron E1. This is efficient computers. Uh, this is our first product we're putting into the market. And the E1 is built around Efficient's fabric architecture. So our mission at Efficient is to build the world's most energy efficient general purpose processor, and E1 does that. We're general purpose. What I mean by that is, we take C++ code, general imperative language code, and our compiler and software stack maps that into our architecture. And our architecture, you mentioned Dataflow. We love
Mhm.
Dataflow. Our architecture is built around the principles of Dataflow. And we are a reconfigurable spatial data flow architecture. And it's in the parallelism of a data flow architecture, our data flow architecture, and it's in the efficient data movement and instruction supply optimization that you get with a data flow architecture that really we manifest the energy savings that I described a minute ago. So, we take general purpose code, and if you compare to other sort of general purpose in market like CPU architectures,
Hmm.
see 1 to 2 orders of magnitude improvement in energy consumption with low or no modifications to the code at all.
Well, that's interesting because how are you implementing the compiler to essentially take advantage of the parallelism that you have in the hardware?
Yeah, that's a good question. So the way our hardware works is so imagine in your mind's eye, picture a grid of what we call tiles, and
Hmm.
that makes up a fabric. And a tile is like less than a processor core. It's not like a multi-core. Kind of runs a single instruction, and there are many, many of those. And we can put an instruction down on a tile, and when the instruction has inputs sitting at the input port to the tile, then the instruction is allowed to fire and it spits out a value and sends it into the on chip network. The on chip network connects that tile, the output of that tile, to the input of another downstream tile. And so this is obviously a bit of a cartoon. I'm abstracting away some details here, but that's the data flow execution model. And what's really cool about that is instructions stay put on their tile for a long time. Could be 10 million cycles. You configure the tiles. The compiler figures out how to do this for you, by the way. Configure the tiles, put the instructions down. And then the compiler also sets up the routes between the tiles. And that's like circuit switching, like the old telephone networks when you would call the operator and they would close the circuit for you, that kind of thing. And that's a very efficient way of moving values from where they're produced when one instruction runs to where they're consumed downstream. The tiles are otherwise uncoupled. So they fire when they want to. We're synchronous. We're not doing any like asynchronous stuff. That's very difficult to design around. But the tiles are mostly uncoupled from one another. And so we have an extremely high degree of parallelism and dynamism in the execution because whenever an instruction's inputs are there, boom, it fires. So on a given cycle, we might see like 75 instructions per cycle. On a CPU, you're like two, maybe. And all of that parallelism is where we have a performance advantage and an efficiency advantage. So to compile for this, we have a compiler and software stack that digests in general purpose C, C++, et cetera, general purpose code, and turns it into a data flow graph representation. There's this intermediate structure that you can derive from arbitrary general purpose code. The representation that we use is, in a sense, is our secret sauce. And that is the result of about a decade of first research at Carnegie Mellon and then 3.5 years of advanced development at Efficient. We've been building this for a long time. And it's that representation that allows us to efficiently map into hardware the way I just described, but also to target something from high level software in a way that is universal and matches the efficient hardware representation.
Now, this sounds a lot like an FPGA and how the mapping occurs, but I think this is a bit different in terms of the size of the blocks. It sounds like you're moving standard data types around as opposed to individual circuits that an FPGA would.
Yeah, you got it. So there is like some, if you squint at it the right way, there's some similarity. You might think, okay, spatial architecture, so it's all the same, but it's very, very different from an FPGA. Internally, it bears almost no similarity to an FPGA. So FPGAs, I mean, I'm sure you know this, but FPGAs were first invented for circuit emulation. You want to put down your circuit and see how it works, and then you can tweak, 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 and then eventually you know what you want to implement in hardware, and you go off and implement it in hardware. And so to support those kinds of functions, there's a lot of configurability inside
Mhm.
of the FPGA. So for example, if you want an 11-bit data path, and then you want somewhere else in your design a 3-bit data path, you bless you, you may have that. um, that doesn't really match the primitives in most software. And so in software, what you're normally doing is manipulating 32-bit values, or if not 32-bit values, then maybe 2 by 16-bit values or 4
Mhm.
by 8-bit values or something like that. And you're usually using, okay, it's float 32 or it's like int 32. And it's not, int 11 or something. That's not really a common format. So the FPGA has a lot of configurability and a lot of little switches inside that allow to configure for all of those funky data transport types. We don't do any of that. Instead, we do what I was just describing. We support primitive data types that are reflective of what people are actually doing in software, float and int, and SIMD with narrow width data types like 16-bit int and 8-bit int. And that covers a really broad spectrum of applications. We're looking at use cases in infrastructure and industrial automation, space and defense, robotics and automotive. And that encompasses things like DSP, search problems, sorting problems, AI problems, computer vision. That all of what I'm describing is covered by that set of data types. And along with those, we have a set of useful, common primitive operations. And
Mhm.
that's what's implemented inside the tile. We don't need arbitrary functions that we can implement in like a lookup table. It's kind of simultaneously over engineered for generality in a sense, because you can put anything you want to inside of your lookup
Mhm.
table. But because of that generality in the FPGA, it's like you pay a tax. And meanwhile, we're fully general. We support all of software and we don't pay the tax because we have an ISA that exposes the operations the software actually uses.
Hmm. Well, it sounds like a much different approach. What does that do for the various data types that you're talking about? Because if you're doing, say, floating point, the kinds of hardware you need to actually do those calculations tends to be large. Is this something where the, the tiles are identical, or do you have specific ones for things like floating point?
Yeah, also a very nice observation about the hardware that we can have different types of tiles sprinkled around across the fabric. And in fact, that's an implementation parameter. Now, the specific mix for a given chip, I mean, that's really neither here nor there for this conversation.
Mhm.
E1 has a particular mix that is well matched to a broad set of use cases in the areas of interest that I described before, especially for signal processing, for kind of general purpose computation. We did a lot of profiling and a lot of evaluation of what's in the market to make sure we had the right mix. Now, the type of operations that we can support and the types of different tiles that we can support, it's things for floating point and it's things for, arbitrary kind of integer arithmetic operations. There's tiles that are dedicated to doing memory manipulation operations. And
Hmm.
so there's a small amount of heterogeneity in the mix of the tiles that makes up the fabric. And it's matched to the types of software applications that our customers need for the types of software that they're running in their use cases.
What about the data movement? Obviously, you were doing some hand waving before, but is this a hard coded routing of things, or is there scheduling movement of packets between things? Can you delve a little bit more in that area?
Yeah, I can. So our network it's not a packetized dynamic network in the way that that question suggests to me. That's not something that we do. Instead, there is efficient communication directly between the producer tile and the consumer tile. And the details of that, some of the details of that are really at the heart of our, the implementation magic inside of our chip. We've got a very efficient on-chip network. And one of the key properties is that that network allows us to do direct producer to consumer data flow communication between tiles. So imagine for a second how you do this in a CPU. In a CPU, when one instruction wants to talk to another instruction, you put a value into the register file. And then on the next instruction, you go and pull that same value back out of the register file. It seems a little bit like Sisyphean, like, okay, we're going to put
Mhm.
this here and then, oh, back down again, right? So you're just kind of there and back over and over again. And that indirect data movement through the register file, it's actually quite expensive. If you look at a GPU, the register file is even larger. Now you have, instead of one operand to be an input for an operation on the GPU, you do a large vector of operations for each instruction. And so you might be fetching, 32, 64, 128 values simultaneously. And then you have to also write back 128 results on the same cycle. And so you're doing a lot of that indirect data movement. It can be very expensive. In contrast, we do direct data movement from point to point, and it's about as low cost as it can possibly be. It's the cheapest it can be because it's directly from producer to consumer.
How much of an application is going to be within the fabric? And how do you handle something that's potentially larger than the fabric in terms of swapping things out?
The fabric is sized to accommodate common subunits of computation. So if you look at an application, you usually have some structure to the application. So imagine like a loop nest, triply nested for loop doing some sparse linear algebra or something like that. Sure, that's very common. We'll fit the entire loop nest onto the fabric. You can always grow this. And of course, there's the thought experiment of, okay, let's make a program that exceeds the size of the fabric. That's where our compiler comes in. And our compiler is very good at optimizing code for the fabric. The first thing that it will do is analyze which of the instructions in this program operate together. And what that means is which operations have a data flow relationship between them. And so it'll piece the loop nest apart in that way and say, okay, here's a subset that communicate, and here's a subset that communicate. Those will become two, we call them configurations, two different configurations. The fabric will be configured with the one configuration, and that might run for 1,000,000 cycles, does part of the work of the loop. At the end of that, the compiler in the program represents the idea that there's more work to do here. The fabric knows how to reconfigure itself. And so it can go and grab the other configuration, pull it in, and then continue the work of the loop. Again, it sits there for another 1,000,000 cycles and does all the work of your loop nest. And at the end, you have the net effect of if you ran the original code as it was expressed. And we can do this for sort of arbitrary large chunks of code, even if it was like some long straight line sequence of code. The compiler is very good at splitting things out to respect the data flow relationship between operations.
Well, I'd like to go into much more depth, but we don't have too much time left. One last thing. Is there a programming language that might enhance the way this works? Or, are we going to be just using standard C or Rust?
This is a really nice question. So I love to see general purpose code running on our architecture. The power of bringing in the entire universe of software. C and C++ is just pervasive. It's everywhere. E1, the Electron E1 processor, is targeted at the embedded domain. Our architecture scales beyond the embedded domain, but we're focused on embedded with our first processor offering. And because of that, the lingua franca is really C. You have a lot of
Mhm.
C code, C++ code. When I think about the future, I think about other more domain specific interfaces to write programs. And we support many of these already. So for example, we have on our roadmap, we have support for Rust. And we have a partial implementation of that now. And I've been playing with it. It's a really satisfying experience to have Rust running on this thing because that's a wonderful interface for expressing this kind of data flow relationships directly in high level abstractions, especially the sort of functional style Rust. It's really natural to represent in that language. Other interfaces go even more abstract and higher level. Things like, for example, the JAX Python numeric computation library.
Mhm.
That's essentially a DSL for doing numeric computations, and it is full featured. It's easy to use. That's on the roadmap too to support JAX. We can take these high level abstract representations and we can put them into the fabric and take advantage of the explicit parallelism that shows up here. So we have made a choice, and this is an important strategic aspect of what we're doing, to bring to the market something that can run code as it is today. The vast majority of code fits the C and C++ idiom, and that's super important for our customers. They can get started immediately. We shoot for like 2 minutes to hello world and 5 minutes to your first application. And people,
Now,
they get that. And that's because the tools work with the existing code. So that's very important to us. But there is, potentially there's a bright future for some of these sort of DSLs and other ways of programming that express more parallelism and a better map to the hardware. Yep.
well, great. Well, we'll have to have you back later to delve into this more because that's a fascinating approach. Thank you.